Now let's take a look at general characteristics found commonly in real-time systems. Most real-time systems are complex and large. They can vary from a few hundred lines of assembler or C to 20 million lines of ADA estimated for space station Freedom. The real-time systems has concurrent control of separate system components. Devices operate in parallel with the real world. It is better to model this parallelism by concurrent entities in the program. Real-time systems has facilities to interact with special purpose hardware. They need to be able to program devices in a reliable and abstract way. Real-time systems needs to be extremely reliable and safe. Embedded systems typically control the environment in which they operate. Failure to control can result in loss of life, damage to environment, or heavy economic loss. Real-time systems must guarantee response times. We need to be able to predict the confidence, the worst-case response times for systems. Efficiency is important, but predictability is essential. Now let's see where we can find real-time systems, or where real-time systems is in use today. First of all, in industrial applications, we can find real-time systems in automated production assemblies and also nuclear power plants and chemical plant control systems. In the automotive and transportation section, real-time systems can be found in autopilot systems, anti-lock braking systems in vehicles, and also multi-joint full injection systems in modern vehicles. In telecommunications, real-time systems are used to control mobile communication devices, satellite antennas, and so many devices which are similar. Modern computer peripherals are controlled by microcontrollers which has real-time systems embedded in it. There are so many medical instruments. Real-time systems control the responsiveness of ventilating machines which are responsible for the survival of patients in critical condition. So many other similar machines are controlled by real-time systems which are used in the recent medical field. As you can see now, real-time systems are almost everywhere around us today, even though it is hard for us to notice them. Now let's consider about what makes real-time systems so significant. Real-time computing is sometimes misunderstood to be high-performance computing, but this is not always the case. For example, a massive supercomputer executing a scientific simulation may offer impressive performance, yet it is not executing a real-time computation. Conversely, once the hardware and software for an anti-lock braking system has been designed to meet its required deadlines, no further performance gains are necessary. Furthermore, if a network server is highly loaded with network traffic, its response time may be slower, but will in most cases still succeed. Hence, such a network server would not be considered a real-time system. Temporal failures like delays, timeouts, etc. are typically small and compartmentalized, but those are not catastrophic failures. In a real-time system such as the PLDCII 100 index, a slowdown beyond limits would often be considered catastrophic in its application context. Therefore, the most important requirement of a real-time system is predictability and not performance. Some kinds of software, such as many chess-playing programs, can fall into either category. For instance, a chess program designed to play in a tournament with a clock will need to decide on a move before certain deadline or loses the game, and is therefore a real-time computation. But a chess program that is allowed to run indefinitely before moving is not a real-time system. In both of these cases, however, high performance is desirable. The more work a tournament chess program can do in the allotted time, the better its moves will be. And the faster an unconstrained chess program runs, the sooner it will be able to move. This example also illustrates the essential difference between real-time computations and other computations. If the tournament chess program does not make a decision about its next move in its allocated time, it loses the game, and it fails as a real-time computation, while in other scenario, meeting the deadline is assumed not to be necessary. Now let's discuss about the relationship between real-time systems and embedded systems. First of all, real-time systems are quite similar or quite related to embedded systems. Now first of all, let's see what is an embedded system. An embedded system is a computer system designed to perform one or few dedicated functions, often with real-time computing constraints. It is embedded as a part of a complete device, often including hardware and mechanical parts. By contrast, a general-purpose computer, such as a personal computer, is designed to be flexible and to meet wide range of end-user needs. Embedded systems control many devices in common use today. These devices include mobile phones, consumer electronics, ATM machines, industrial machines, and so many other things. Almost all the electronic and electrical devices used today are controlled by microcontrollers or digital signal processors, which has embedded systems as their controlling system. These include mobile phones, electronic games, consumer electronics, and simple electronic devices like ATM machines. So as you can realize now, there is a very close relationship between real-time systems and embedded systems, and they are often considered to be the same thing. That's all we are going to discuss for the part 1 of the video. Hope this has been useful to you. Please do join with us for the part 2 and the more advanced topics of real-time systems. Have a nice day.